So I will just share screen. I think you have to allow me to share screen.
Oh, okay. Yes. I think you have two.
It's the one where I have the video.
Okay, can you share?
I see. So here it is. Here we are. Okay, good. So first of all, G, thank you so much for the kind invitation, and it is a pleasure to be speaking in this lovely seminar. I hope sometime I can visit in person and give the seminar in loco. So today I'm going to speak about this notion of Kähler bands, which is actually quite natural in the context of Chern insulators. And I'm going to talk about when one considers the idea of holomorphicity in this context, which is natural when one wants to go from the non-interacting setting to the interacting setting. And I'm also going to speak about the induced quantum geometry. Okay, so to begin, to motivate, I will speak about coherent states and the associated Kähler geometry. And then I will proceed and speak about fractional Chern insulators and Kähler bands in this context. Okay. So let us consider bosonic coherent states. They are defined by the following equation. A here is a bosonic annihilation operator, and Z is a complex variable. And so you have this equation, and one can define a fully holomorphic representation of this state or family of states, which is of this form. And the first thing that you see is that the right-hand side only depends on the variable Z and not on the variable, on the complex conjugate. The thing is that if you use this parameterization, you notice immediately that the state or the vector is not normalized to 1. So you have this normalization that appears, and this is a common feature that will appear later. Okay, very good. So this is a holomorphic family of states, and from this you can, by pullback of the Fubini study structure, and actually other structures, so some connection, the line bundle over CPN, actually infinity. You have the Berry connection, which looks like the derivative of the logarithm of this normalization. And you see it's a 1-0 form, so it only has dz. And then you have the Berry curvature, which also assumes the form of a second derivative or a derivative of the normalization here. Besides, you have the quantum metric, which is the pullback of the Fubini study metric, which also assumes a similar form with these second derivatives of the logarithm of the normalization. Okay, very nice. If we introduce phase space real coordinates, Z equals to X plus IP, then we have a triple of structures, which I compactly denote here. So in the left hand side, I write it in form notation, and in tensor notation. In the right hand side, I use matrix representations. And you see you have this object omega, which is -I/2f, which plays the role of a symplectic form. Okay, and you see that this is the standard symplectic form that appears in classical mechanics. Then you have this Riemannian metric. And then you also have this object, which is associated to this complex variable here. And you can think of it as giving the phase space a complex structure. So you can see that this matrix is clearly a rotation of 90 degrees in the plane, and it squares to -1, just like the imaginary unit. And these three structures are compatible, and this compatibility condition is seen by this matrix equation here. Okay, so this I will refer to this as a Kähler condition. This just means that these three structures form a compatible tree. And these three structures give C the standard structure of a Kähler manifold. Okay, so let us proceed. The other thing is that the fact that the Berry curvature is non-vanishing means that if we take the state and we adiabatically change the state, according to the adiabatic theorem in quantum mechanics, if we adiabatically change the state along a loop based at some point, that is the boundary of some region in the complex plane, then we will have a Berry phase, which is which assumes this form here. It's the integral of the Berry curvature on this region. And from this relation here, we learn that this phase corresponds to twice, and this is just a geometric factor, the phase space area as measured by the symplectic form of this region here. Okay, let us continue. So now let us move on to a different example. Let us consider spin 1/2 coherent states. They can also be defined through a holomorphic formula. So here, sigma minus is the Pauli matrix, sigma minus, okay? And you see that, again, the right-hand side only depends on the complex variable z and not the complex variable z bar, okay? So holomorphicity is again here. Well, the complex variable z is z is only a complex variable in C, but because states are only defined up to multiplication by non-vanishing scalars, there's an extra state at infinity corresponding to the up to the down state, if you want. So you actually have a family of states parametrized by the Riemann sphere. Okay, so let us continue. So now you have a holomorphic family of states, of quantum states parametrized by the Riemann sphere. And if you pull back the Fubini-Stelli structure, and also the connection on the tautological bundle, basically, you have this Berry connection, which again is the derivative of the logarithm of the normalization. Notice now that there appears this 1/1 plus modulus z squared. And you have the Berry curvature, which again assumes the same form as before, and the quantum metric. And you see that these two objects, well, they basically look the same up to exchanging the symbol of wedge by the symbol of symmetric product. Okay, so if we introduce the Sander spherical coordinates for which z is this stereographic projection with respect to the south pole, so theta is this angle that comes from the z-axis and phi is the angular variable. So we have a triple of structures, omega, j, and g, as similar to what happened in the plane. And again, I will not bother you with the details of this, but they are compatible. So you have, if you write in any local coordinates in the sphere, if you write these three matrices, you will find that this formula holds. Okay. Okay, and basically this gives the Riemann sphere the structure of a Kähler manifold. Here we are in the compact setting, and we also have the first glimpse of topology, the first Chern number. So if you look at the Berry curvature, you see that essentially this field here corresponds to, can be interpreted as the magnetic field of a monopole sitting at the origin of R3. And you have an associated topological charge, which is essentially the first Chern number of a certain bundle of, well, the bundle of states that you have over the Riemann sphere. And it is -1 in this case. And because of the Kähler condition, if you take determinants and square roots, what you find is that there's this relation between the symplectic form and the Riemannian volume element, essentially. And what you find is that the Berry curvature satisfies this identity here. And integration gives you this relation between the left-hand side, which is a topological quantity, and the right-hand side, which is a geometric quantity. So here, vol G means the volume as measured by the quantum metric. Okay, so this is the first instance of where here it is an equality. Topology on the left-hand side and geometry on the right-hand side. Okay, so what was the crucial ingredient in this construction? Well, the coherent states are holomorphic with respect to a complex variable. Actually, you have a complex structure, so locally only complex variables. With respect to a complex variable in the base manifold, which here was either in the first case, it was the complex plane, it was a phase space, the standard phase space, or in the second case, it was the Riemann sphere. This had as a consequence that the Berry gauge field assumed this very nice form. Essentially, this is referred to as a Chern connection on a bundle because it assumes the derivative, this special form here. And what happened was that this quantity here, which I refer to K, the logarithm of the normalization became a Kähler potential for this symplectic form, and also the metric was the second, essentially related to the second derivatives of the Kähler potential. Okay, so before we move on, and because we're interested in Chern insulators, it will be convenient, by the way, if you want to ask questions, please stop me at any time, okay? Because we're interested in Chern insulators, let me introduce yet a third holomorphic family of states. Right now, it will be the UN coherent states, and I will call this family the Fermi C family for physical reasons. And so in this setting, let us consider Z to be a rectangular n minus r times r matrix. And we consider a Fock space composed where you essentially have n fermionic modes. Okay, so these C daggers are creation operators for fermions, and you have n of them, and you create the first R ones above the vacuum, and then you rotate with this matrix, with this operator here. There's this nice relation between the exponential of this and this matrix on the right-hand side. And essentially, this might look a bit mysterious now, but if you introduce holomorphic Bogoliubov quasi-particles by the following formula, okay, so you have, it's essentially the first R, you have R fermionic quasi-particles, which are obtained from the old ones by summing this combination, this linear combination of the remaining ones. And if you do this, because I wanted to have some holomorphic structure, you will find that the commutation relations are a bit modified, but that is no problem. And you will find that this state Z can be obtained by creating this fermionic mode above the vacuum. And that's why I called it the Fermi C. Okay. So this matrix Z essentially parameterizes subspaces of dimension R in CM. So basically it has to do with these R modes that I'm generating. And they label the states below the Fermi level of a flat band Hamiltonian, which I write like this, over a z-dimensional, over a zero-dimensional lattice. So essentially it's a blob, a lattice without structure, so a point. And you have, and this matrix Hij is essentially a flat band Hamiltonian that you construct out of the projector, out of this projector, which is built of the matrix Z, okay? So essentially, our dimensional subspaces of Cn are in one-to-one correspondence with this projector here, and Z is a complex coordinate labeling those R-dimensional subspaces. So the family of states that you are creating is essentially equivalent to Slater determinants with R particles. And the base manifold is the Grassmannian of R planes in Cn, which are linear subspaces of dimension R. Okay, so then you can play the previous game that I told you, which is to pull back the Fubini study structure, and you get an induced quantum geometry, where here the Kähler potential assumes this form. Okay, and the symplectic form again is the derivative, the second derivative of this scalar potential, but it can also be written in terms of these projectors. And the same for the quantum matrix. So with this, I can now move on to the main topic of this talk. So let us.
Sorry,
proceed.
may I stop and ask a question?
Oh yeah, please.
Yeah, I think the Fermi surface is very interesting. So usually, to define the Fermi surface, we need single particle dispersions such that we have a chemical potential, so particles whose energy is smaller than chemical potential is occupied. In this way, we define a Fermi surface. And
I understand.
And,
so here what happens is that this Hamiltonian, let me put it like this, is just has it has two flat bands with energy +1 and -1. And essentially what I'm doing, so it's an insulator essentially. I'm putting the Fermi level at 0, and I'm creating all states in the lower band. That's it.
So the lower band is fully filled, so it's an insulator.
It's an insulator, yes.
Okay,
yes.
but the point here is
so maybe Fermi C is not the best, not the best notation, but yes, yes.
I see. So the physical meaning of the Zij is, what is the physical meaning of the Zij?
Of the Hij, this matrix?
In the slides, one slide back.
One slide back?
Here? Yeah, here in the, you define the Z in the first equation. In the first equation.
So
yes.
this here is completely equivalent to this.
Okay.
These two states are the same. So this is just a different way of writing that state. But the thing is that this is the way essentially Parallelmov would write this state, because what you have is kind of a group, which is the UN group, which acts on these Slater determinants, and it generates all possible Slater determinants. And essentially, you can this description here isolates the fact that this co-adjoint orbit of this group through that point is a Kähler manifold, and this Z are basically complex coordinates on that. So that's the mathematical answer for why I wrote this like that.
So you mentioned you have a two-band system. You fully fill the lower band. So the degree of freedom of the lower band is parameterized by R here.
Exactly. So R is the dimension of the number of states on the lower band, yes, and Z parameterizes all possible such.
So N minus R is the degree of freedom of the upper band. That is empty.
Exactly. N minus R is
okay.
Exactly. So you would also see the Grassmannian here as use of N quotiented by use of R times use of N minus R. That's also another presentation. Good.
So if I have a two-band system, I fully fill the lower band, I should have a unique many-body state. But here you're parameterizing the state with a variable Z, which means that the space is larger than 1, the dimension of the space.
No. So what happens is that suppose that you set n equals to 2, and you exactly as you say, and r equals to 1. So what you get is essentially the Grassmannian of one subspaces of dimension 1 of C2, which is CP1 or the Riemann sphere. And you get back, so essentially what you get is that this Z is parameterizing your Bloch vector on the Bloch sphere. So that's it. And the states are not unique. You have as many as the Bloch sphere. So that's idea. As you change n in the Bloch sphere, you get a different state.
I see. Okay.
I think it will be clear afterwards when I consider Chern insulators. So
okay.
But
okay. Great.
Good. So is this okay?
Yes. It's
okay,
please go ahead. Yeah.
Good. So let us continue. So now let us consider, as I said, the setting of Chern insulators. So suppose we have a Chern insulator in 2 dimensions, and this is described in second quantization by a quadratic Hamiltonian, where you have a single particle matrix, which is this h of k here, which depends on the variable k, which is momentum in the Brillouin zone, which mathematically is a torus, okay? Because you have to identify momenta that differ by reciprocal lattice vectors. Okay, so the occupied bands are, again, they are essentially described by something which I call the Fermi projector. I'm not sure if this is the standard terminology, but essentially it's the orthogonal projector corresponding to all the bands which are below the Fermi level. Okay, and for each, so essentially for each momentum in the Brillouin zone, we have an R-dimensional subspace of Cn. I'm assuming that this matrix H of k is n by m. N is the total number of bands in the system, which is determined by the range of this projector, or the image as a linear space of this projector. And it can be described, as before in the example I gave of the Fermi C family, by a complex Rn. So what is it? It's n minus r times r matrix Z. Okay. The collection of these vector spaces defines a vector bundle over the Brillouin zone, which people usually refer to as the Bloch bundle. So it's the occupied Bloch bundle. And also note that this piece of K, because the Grassmannian of R subspaces of Cn can be seen as the space of all orthogonal rank R projectors in Cn, then this defines a map, the projector defines a map from the Brillouin zone, two-dimensional Brillouin zone, to the Grassmannian. Okay, continue. So this is just an illustration of this Bloch bundle. So you have a point in the Brillouin zone, and over it you have a vector space of dimension R. And then now the relation with the previous example should be more or less clear, because the ground state of the insulator is formally the product over all momenta in the Brillouin zone of creating all states which are below the Fermi level. So this here, this piece is essentially this Z of K, where Z now depends on K. So Z was a free parameter before, but now Z depends on K. So essentially, you can see this as a pullback operation, something like this. The state Z of K is a Slater determinant of Bloch wave functions, okay, for the occupied bands. And from this, you can see that you have an induced pullback quantum geometry in the Brillouin zone, which is given by the pullback family. And what you get is a Berry curvature, which assumes this form, the quantum metric, which assumes that form. And also, because we are in 2 dimensions, we can also define a complex structure in the Brillouin zone, assuming that this quantum metric is really non-degenerate, but let us assume that this is the case. And how do you do it? Well, first you pick an orientation in the Brillouin zone, and then you pick an orthonormal frame for this metric at the point K, and you declare that the complex structure is a rotation of 90 degrees with respect in that frame. And what you can, because you are in two dimensions, this is actually well defined and independent of the choice that you did, as long as you chose a frame which was consistent with your orientation. And that's it. Now, the thing is that the triple of structures that you get here is, in general, does not define a Kähler structure on the Brillouin zone, because what you will find is that this condition is no longer satisfied with equality, but rather you have an inequality. And as a consequence of this, if you integrate both sides of this equation, you get that the quantum volume, meaning the volume as measured by the quantum metric, is lower bounded by this first Chern number. On another, this is actually an interesting inequality, at least I find it interesting, which is that if the volume of the Brillouin zone is smaller or equal than pi, then you can only have that the first Chern number is 0, which means that your insulator is adiabatically connected to the vacuum. This is an interesting point. So now we have shown recently that the equality is satisfied for Kähler bands. And we define these Kähler bands to be Chern bands for which the map P from the torus to the projective space, or to the Grassmannian, sorry, is holomorphic, okay? In that case, what that actually means, put in simple terms as possible, is that we can find a holomorphic representative for this state here, meaning that we can choose a local holomorphic coordinate on the torus such that this holds, okay? In that case, the triple of structures that I have introduced previously turns the Brillouin zone into a Kähler band, okay? Proceeding, so now that we know what Kähler bands are, let's consider fractional Chern insulators. So fractional Chern insulators are lattice realizations of the fractional Hall effect phase. In the setup of the fractional Hall effect, one usually assumes a large magnetic field such that the Coulomb interaction does not mix Landau levels, but it mixes states within the Landau levels. And for filling fraction mu equals to 1 over m, where m is an integer, one then considers as a good approximation for the effective Hamiltonian this density-density interaction, where these rho bars are the projected density operators. So, of course, one of the features you see is that there is no kinetic term because you projected to lowest Landau level. And another crucial ingredient, which is not described above, is that the projected density operators, they now satisfy the so-called Girvin MacDonald Platzman algebra, which is this algebra here. Here B is the magnetic field strength, and Q and Q1 and Q2 are momenta. And you have this relation here, which is a quantum version of the algebra of area preserving diffeomorphisms of the plane. So this is an important feature. So the usual folklore is that if we have a dispersionless Chern band together with density-density interactions, such that projected density operators satisfy an algebra which is at least isomorphic to the one above, then we can realize a fractional Chern insulator. So this is more or less the background. And the thing is that if the Chern band is scalar, meaning that you have this saturation of this inequality that I wrote before, and also flat in the sense that it is translation invariant in momentum space or uniform, then the Kähler triple of structures, actually G1 knows that there's actually a refinement of this condition, but then the projected density operator satisfies such condition. So if it is flat, then this holds. And this is actually a restatement of a result by Raoul Roy. And now from this, what I'm going to tell you is how you can actually engineer these flat Kähler bands, at least in asymptotic limits. So the way we're going to do this is with resort to geometric quantization. So, okay, I'm speaking ahead. we're going to use geometric quantization and Bergman kernels to engineer flat Kähler bands. So roughly speaking, geometric quantization is a way to assign a Hilbert space to a phase space in a physically and geometrically sensible way. For us, this phase space will be our Brillouin zone, momentum space, and the Hilbert space will be an auxiliary vector space of holomorphic sections of a certain line bundle, which is called the pre-quantum line bundle, from which we'll be able to build the Kähler bands. Okay, so now let's do this. So let us think of the Brillouin zone as the plane, R2, where we identify momenta that differ by reciprocal lattice vectors. And then if we set tau a complex number with positive imaginary part, then 2 pi z, which is k1 plus tau k2, defines a periodic complex coordinate on the torus. And we will write z equals to x plus tau I for convenience. And this is an illustration of the fundamental parallelogram. Then this gives the Brillouin zone the structure of a complex torus, where lambda is this lattice here, determined by 1 and tau. And it can be shown that all Riemann surfaces, that is complex manifolds of dimension 1, they are isomorphic to one of these forms. Okay. The structure of holomorphicity is very, very rigid because it involves convergent Taylor series at the point. And in particular, only holomorphic functions, the only holomorphic functions over this complex torus are the constant ones. The story gets a bit more interesting if we consider meromorphic functions, which up to scale are completely determined by their zeros and poles. There is a generalization of the notion of function, which also gives non-trivial results. And this is the notion of a holomorphic section of a holomorphic line bundle. And this will be the main object of interest now. The prototypical example of this is Jacobi's theta function, which is this given by this series here. And it is a simple exercise to show that under a translation of the lattice, you have this transformation formula. Okay, so you translate a bit and you get a phase, a gauge, which you can think of as a gauge transformation, which assumes this form here. And these gauge transformations, they have to satisfy a cycle condition, but which I'm not going to write here. But essentially, they define these rules. They define a holomorphic line bundle over the complex torus, which is given by the quotient of the trivial bundle over the complex plane, by the action of the lattice by translations. So you have a pair, which is a z, which you can see as a momentum, and then you have v, which you can see as the amplitude of the wave function, and the action of a translation is translate the momentum and multiply by gauge transformation. The theta function that I wrote there, the Jacobi theta function, is the unique up to scale holomorphic section of this bundle. I.e., it is the unique function which is holomorphic and satisfies this transformation form. And the theta function has a unique simple zero over the torus, and one can show this by computing its integral, the integral of the logarithm. And actually, what you're computing is the first Chern number of or degree of this line bundle. We can, furthermore, on this line bundle, we can introduce a notion of inner product. I'm not going to bother you with this, but essentially you can just, you just need to introduce a function such that this quantity is periodic, meaning it defines a function on the torus. And you can find solution of this form here if you go through details. And from that, you can build a gauge field by taking the derivative of logarithm. You have curvature, and what you see that if you multiply curvature by I, you find a symplectic form on your torus. And what you now have is a Kähler manifold, which is a complex torus, this symplectic form, the complex structure as determined by the complex variable that I wrote, z equals to x plus tau I. And you have a metric which is given by compatibility. Okay, so you have a Kähler manifold. And essentially the condition that omega is equal to IF, where F is the curvature, is the geometric quantization condition. This bundle that we wrote, the theta, the bundle associated to theta, is known as the pre-quantum line bundle. And this vector space that you obtain by making the span of this theta function is the quantum Hilbert space associated to geometric quantization of the Kähler manifold, complex torus at level 1. And this is a nice building point. You can then generalize this construction by considering tensor powers of this line bundle. And these bundles will have a Chern number P, where P is a positive number, integer. And again, you can play the game of looking at for holomorphic sections of that bundle, where now you have this twisted transformation property. So you have the previous case transformations, but multiplied by P because you're taking the Pth power. And you have a convenient basis of solutions for this problem given by Jacobi theta functions with rational characteristics. So this is the formula for your convenience. But now notice what happened is that instead of having just one solution, you have P solutions, okay? So you get a vector space of dimension P consistent with the Chern number that you would get. And one immediately sees that since h to the P provides an Hermitian metric to here, now the curvature is scaled by P. And what you did was to rescale the symplectic form, basically. And this line bundle is now our pre-quantum line bundle, and this vector space, which you obtain by spanning these functions, is the quantum Hilbert space resulting from geometric quantization of the Kähler manifold at level P. So before introducing the Kähler bands, because we're almost ready to do that, I just want to point out that it's very interesting that this is also appears in Chern-Simons gauge theories. So when you want to quantize a Chern-Simons, what happens is that the Kähler quantization of complex story appears there. U1 Chern-Simons theories. Here our P that I had in the previous slides is 2 times kappa. Kappa is the constant that appears multiplying the Chern-Simons action. And our complex torus, which was the Brillouin zone, is the torus of flat connections on a real torus modulo gauge transformations. The quantum Hilbert space of the theory, which results from quantization, is roughly this space of theta functions. Well, not exactly, because one actually has to take into account the determinant line bundle, but we do not care about this here. So another point is that this quantization can be shown to be independent of complex structure via methods of geometric quantization. And this is actually something I would like to explore, but this talk is not, it's out of the scope right now. So this all seems nice, but what about the Kähler bands? Well, since we have that our holomorphic sections are given by lambda equivariant, lambda being the lattice equivariant functions, then if we choose a basis for this vector space of theta functions, we have a well-defined quantum state given by this linear combination, where these i's are a basis of this CP, a vector space of the same dimension of this. So what you see is that if you translate K by a reciprocal lattice vector, since all these functions transform in this way, what you get is a phase is a phase multiplication from the previous. So this, since quantum states are defined up to multiplication by non-vanishing scalar, it follows that this family of quantum states described like this is well defined. And by construction, this family is immediately holomorphic in the complex variable because all the functions involved in the construction are holomorphic, right? And it defines, so for each P, we have a holomorphic map from the complex torus to the projective space CP -1, right? Which is indexed by the Chern number of the pre-quantum line. And these are the desired Kähler bands. So this is the bands that I want to use. And what you see, if you compare the symplectic form P times omega to the Berry curvature of corresponding to this family of quantum states, you get a relation of this form, P omega minus IF is equal to the second derivative of the logarithm of B. B is a very special function, which is given by this quantity, and it is a smooth function on E tau. And furthermore, this relation here that I wrote of the symplectic form with respect to the Berry curvature also holds for the quantum metric and the metric which was compatible with this symplectic form. And the reason is because the map is holomorphic, everything is scalar, everything is compatible. Okay. So for the particular case where these functions fi's are an orthonormal basis of this space of theta functions with respect to this L2 inner product, then the function B is the diagonal of the so-called Bergman kernel, and the latter is known by the works of Zeldich and others to have a large P asymptotic expansion of the form B equals to P, a constant, which is the Chern number that you started with, and then some functions like this. AIs are smooth functions which involve invariance, geometric invariance of the pre-quantum line bundle and the manifold. What you see is that because of the relation above, as P goes to infinity, the Berry curvature goes to P times omega. And then because omega was translation invariant, so will be F in the asymptotic limit when P goes to infinity. So again, because the mapping is holomorphic, the same will hold for the metric. It will become translation invariant. And actually, there's a nicer interpretation of this, is that I'll say this later.
May I stop?
Please.
Very simple question. So P here is a degree.
Yes, it's the degree of the pre-quantum line bundle. Yes.
So the Chern number, what is a Chern number?
So in that context, the degree and Chern number of pre-quantum line bundle are the same, but the Chern number of the Kähler band will be minus P. It's different because the pre-quantum. So what happens is that the pre-quantum line bundle will be isomorphic to the dual of the bundle that you obtain by pulling back the tautological one.
So in the context of quantum Hall physics, P is the n phi, phi is the number of flux you have.
Something like this, yes. Yeah, exactly.
So another question is, when you mentioned Bergman kernel and you mentioned the large P asymptotics of this Bergman kernel, is there any like exact statement at finite P about, because do you have more comment about Bergman kernel? As far as I know, it is about the overcompleteness of the holomorphic basis.
So right now I can. So what is the question? Why does the Bergman kernel appear?
Yeah. So what is the definition of Bergman kernel, and why do you need large P expansions?
So the large P expansion is to get the flatness, because I want to construct flat Kähler bands, right? And the reason why the Bergman kernel appears is because the Bergman kernel is the projection of the space of sections onto the space of holomorphic sections. And actually what this quantum state here that I built is something which is related to that. It's essentially the Kodaira embedding of the surface on the projective space. So it's natural that
So you look at the large P expansion, and the motivation is you want flat Kähler.
Flatness, exactly.
So if I don't, if my motivation is a general Kähler band,
you can do finite P, yes.
Yes. Yeah, okay. So the Bergman kernel is well defined as long as you have this holomorphic.
Oh yes,
Yeah. Okay. Okay. Yeah. Thank you.
I will make a further comment on this in the end, but very good question. Thank you. Now I give you just some numerical results on the flatness. So here what I plot is the Berry curvature in the K-space for different values of P and for different values of tau. And what you see is that, so P equals 2 is orange, P equals 4 is blue, and P equals 6 is green. And what you see is that as I increase P, the flatness of the Berry curvature is immediate almost. I mean, it goes very quickly to flat. And the exact same values occur for the square root of the determinant. So you can consistently see that these are indeed Kähler bands. So the next thing, and finally on this subject, is that we can construct tight binding models for this. And the way you do it is by writing down the projector associated to that quantum state that I wrote. And this gives you a flat band Hamiltonian again, where there are two bands, one with energy +1, the other with energy -1. The -1 band is exactly your Kähler band. And then you can basically write a tight binding model by just Fourier transforming to real space. The only problem with this is that these models are not very physical because, and this will be realizable in the lab, because they involve infinite range hoppings, because you see the theta functions have an infinite, is given by infinite series. And it is natural to ask what happens when we truncate the hoppings to nearest neighbors, next to nearest neighbors, and so on. And if you do this exercise, here I plot, of course, I plot the quantum, the Berry curvature, and the square root of the determinant of quantum metric, and you see that also because by convenience I also plot in a cut K2 equals 0 because these plots are a bit hard to understand. But what you see is that as soon as you start increasing more and more neighbors, very fast you get very similar results. But I should make a few comments. So as soon as you truncate the hoppings, you break holomorphicity because you need infinite range hoppings to get holomorphicity. However, the difference between square root of the determinant and the symplectic form is not so large, even for nearest neighbor. So it's a good approximation. So there's hope that you reproduce the same properties, and the flatness of geometrical quantity changes. Geometrical quantities will not become more dispersive, and sometimes they can even become flatter when truncating the hoppings. This is something which we found puzzling. Another important remark is that when r equals to 1 and r equals to 2, the Chern number is already the same as r equals to infinity, and this happens for all other r's. And what this means is that your band is adiabatically connected to the Kähler band that you want. Okay, so they are in the same topological class as they should be. Okay, we have also numerically checked the cases with smaller p. So the plots here are for p equals to 6, but we have also checked for other p's, and the behavior remains the same. Another thing that I wanted to say is that in this paper with Tomoki, we have also shown the no-go theorem that it is impossible to construct exactly flat Kähler bands with a finite total number of bands from a holomorphic map like this. And the reason is that if you want flat, this is the remark I wanted to do. If you want flat Kähler band, you want translation invariance, and so you kind of need to look for the isometry group of this Kähler manifold, which is the unitary group. The unitary group UP, and so you use of P. And you want to realize the translations, the infinite translations, as unitaries here. And if you do that, you will not be able to do this. And actually, what happens is that for the bands that I constructed below, what you can realize is a finite, well, projectively at least, is a finite cyclic group, which is the Heisenberg group, which is it lifts to the Heisenberg group, finite Heisenberg group. And what happens is that these scalar bands will have a symmetry, but it will not be full translation symmetry. It will be a smaller, only rational translations will be symmetry of these scalar bands. And so now I want to tell you a little bit in the last minutes. I have we have some work in progress along these directions. So we have shown that the method presented above here is actually quite general and essentially unique in approximating the lowest Landau level in the plane by Kähler bands embedded in systems with finite total number of bands. So actually, this construction that I gave to you is actually on essentially unique up to unitary reparameterization. And additionally, the above construction also works for the case of even dimensions, arbitrary even dimensions. And in that case, what you will have is a complex torus equipped with a Kähler structure. And what you will have is maps from the holomorphic maps from the complex torus to some projective space. And what you will find is, if you work out the details, is that the GMP algebra that you get is slightly modified. This is also work in progress. And if you want to read more, please go through these papers with Tomoki Ozawa, the papers that I did with Tomoki. And I also want to give a big thanks to João Pimentel Nunes and José Mourão for fruitful discussions. So thank you very much for listening to me.
Thank you very much. May I ask one question? You mentioned high dimension.
Yes.
Can you introduce mathematically how is two-dimension different from high dimension? What's the motivation to look at high dimension?
So the motivation that I have, well, first, from mathematical side, it is natural to think about this. What you have, you will have theta functions in higher dimensional complex tori, which the theory is completely analog to this. But then the question that I ask is, look at the algebra that you get and see if this can have some exotic, interesting phases, because from what it is my understanding, but by no means I'm an expert in this, that the GMP algebra gives rise to the interesting phenomenology into dimensions. So it would be interesting to understand what happens in higher dimensions if you get a generalization of that algebra.
Mm-hmm.
That's my motivation.
Thank you. Yeah, Hank, you can unmute yourself.
Yeah, thank you for the very interesting talk. So I have just a very basic question. First of all, like is P related to the M, like the fraction of the fractional whole stuff?
No, not here. So actually, concerning that, G1 was also asking what was the relation of P to N phi, the number of fluxes, right? Something like this. So what happens when you try to consider approximations of lowest Landau levels, the lowest Landau level in the plane by Kähler bands, as we do here, as we consider here. What happens is that you have a degree of freedom in the continuum, which is the momentum k, right? And you also have the position in the unit cell, the unit magnetic cell, and this P here, it will actually disappear from the description, because the Heisenberg group that I was mentioning before will make it so that this map here, well, let's put, where is the map? Where is the map? This map here, it will actually descend to another map on another torus, but which is a smaller version of that torus. So it's like it is rescaled by 1 over p. So in some sense, the first question you ask is you are creating bands which have Chern number p, which is a very high Chern number, and you want p to go to infinity. But the point is that we know that the Landau levels have Chern number 1. Each Landau level has Chern number 1. And what happens is that this map will descend to a smaller torus, and when you do the quotient, it has Chern number 1. That's the idea. So the relation of the Chern numbers and the so answering your question, it has nothing to do with the filling fraction. It has only to do with the Chern number of Landau level. That's it. Is more or less satisfactory.
Yeah, so Samuel, you can unmute yourself.
Hello, thank you for interesting talk.
Hi, I'm a huge fan of your work. It's very nice to see you.
Yeah, the interesting papers, yeah. So I have maybe actually a comment about P. I don't know if it's relevant, but for finite P, there exists this metric called the valence metric. And it was introduced by Bourguignon Yao and Donaldson. If you want B to be just constant, that's exactly the definition. I don't know if it's relevant. It makes the density constant everywhere.
I see.
Where exists metric, it will not be flat, but it will be some metric which makes B constant.
I see. This is something that I should look at because also I remember...
Yeah, on the torus it's actually constructed, I think, in some paper. Maybe not on not in many situations, but there are some examples.
Thank you. I will look at that.
I wonder in high dimensions, so most tori would not admit holomorphic embedding.
Right.
That's the physical condition that it's an abelian variety. What it will be.
Exactly. So that's why we move instead of considering torus in general. We already start from the geometric quantization point of view, where your torus is admits a pre-quantum line bundle, which I guess it's related to that in some sense.
Do you have some physical kind of relevance of this?
Of this condition? Not right now, but that's something very interesting to ask.
Yeah, it's an interesting question. And what fails? So I didn't exactly understand. In the beginning, there was a inequality, which failed to be equality.
Yeah, exactly.
So what happened?
I can tell you what happened. So let's go. I guess it's let us. Sorry about that. It's this should be this inequality, right? So this is an inequality that appears naturally. I suppose you're familiar with Wirtinger inequality in Kähler geometry. So this is just Wirtinger inequality. So if you have an embedded submanifold, you'll have an inequality between restricting so suppose you have Kähler manifold and then you have a submanifold of even dimension there. If you restrict metric there and you look at symplectic form, you'll have some inequality, more general than this, but you have some kind of inequality. And the equality only satisfied when submanifold is complex. And Kähler. Yes.
That's okay.
Yes. That's so this is just the Wirtinger inequality stated in different
restricted to 2 dimensions.
Exactly. In higher dimensions, you'll get some exterior power, which is then related to Chern character of some line bundle. But it's interesting.
Okay. Thank you.
No, thank you.
Hi, I have a question.
Please.
So it's kind of like a general question. So can you relate your work to get a lowest Landau level or even higher Landau level for a general curved space? For example, we have a metric and we wanna like get a Landau level wave function in that metric. So can I use your, for example, paper to get this?
So the question goes in line to something that we are working on now. So,
Yeah, I guess like it just gives me the idea that like for example, can you relate your work? For example, we have a metric and we want to get a Landau level on that metric. So is a curved space.
Yes, it is related to that. Yes. So the constructions that we have here, you can relate to lowest Landau level in the plane with certain translation invariant metric. Okay, and you also need a uniform magnetic field. And so the idea is you pick a translation invariant Kähler structure on the plane, and then you can relate to these things. That's the answer to your question. But I guess that you can do better than this for other Kähler structures. But right now, I only know how to do for the translation invariant ones. Does this help?
Yes, thank you.
Oh, thank you.
Can I ask a question?
Yes,
Yeah, please.
How do you construct the Chern density?
Hi, Doug. I know
yeah,
you.
yeah,
It's
of
very
course.
nice to see you.
Yeah.
I don't see you. I only see your picture. But
yeah, sure. So I have a question. You said that with this inequality become equality, you can prove the GMP. So how this happen?
so sorry, I didn't understand you
I
very well.
mean,
The sound was a bit.
Yeah, so you comment that if inequality become equality, that you can have the GMP algebra.
With care, right? So if the inequality becomes equality, then you have Kähler bands. But to have really algebra isomorphic to GMP, what I said in this talk is that you need a uniform. So you need the Berry curvature.
You have the uniform Berry curvature.
But you can do better. You can do better. Ji-Wang has been working on this. If the metric is conformal to meaning by up to a conformal factor, which is related to the Berry curvature, to a flat metric, then you can also have GMP algebra. So I think that's the most general you can get.
Yeah. So maybe
am I right, Ji-Wang?
Yeah, maybe I can comment a little bit. So we have a new paper appeared yesterday, exactly address this question. So the statement is, as long as we have a constant Kähler structure, we allow Berry curvature to be arbitrary non-uniform. And we show that, so first, the wave function has a unique form because the momentum space Kähler structure highly constrains your wave function. And then you can compute density operator explicitly. And we did that, and we found the density operator also satisfying an exact GMP. So we are not assuming constant Berry curvature, but we assume constant Kähler structure.
So basically, you construct the density from the wave function using the density equal to sum of some delta function of z minus zi, something like that, right?
Not. It's where the density operator is the standard density operator. It's e to the iqr. I is the position operator, and projected into the flat band. Yeah.
I see.
Yeah.
Okay. Thank you.
Thank you. Mm-hmm. So any more questions?
Yeah, can I just ask about like just towards, have you been thinking towards like a generalization to fractional quantum Hall, and maybe possible relations to like stuff that's been done by Belisard and Marcoli, like the orbifold stuff?
That's very interesting. It has a different flavor, right? So you want to consider this construction in the equivariant setting or something like this? Is that?
Yeah, exactly, yeah.
But right now, I don't know how to answer that question, but it sounds very interesting.
Okay.
Right. So you're referring to works by Belisard
And Marcoli, Matilda Marcoli. Yeah.
Could you please send me those references? That would be
Sure, yeah. And there's also another paper by Tiang where they constructed, like using, as you said, the equivariant, essentially equivariant twisted K theory to like on an orbifold to reconstruct like the fractional Hall conductance, essentially.
I see.
Yeah.
It's very interesting.
Yeah, and then they claim that. Yeah, and then
Mhm.
they claim that this is like, this should be the underlying geometry for fractional quantum Hall, but
I
yeah.
see.
I mean, because
So
here
something what happens here
Yeah.
when I mentioned the approximation of the lowest Landau level. So
Right.
there's a P appearing everywhere, and because there is a Heisenberg finite Heisenberg group action, the P gets divided by P, and it gives you the Chern number 1 Landau level in the end of the story. But some sense when you have some action and you work in the equivariant setting, you recover. Well, you get this division by things, but that's very interesting. Thank you.
Yeah, and I think the fact that you can actually write down, like you can actually construct a Hamiltonian, even just in the momentum space, I think that's I really want to see that from like from the the Marcoli Belisard perspective, because I haven't seen that anywhere.
So here the Hamiltonian is really just the Hamiltonian that I mentioned in the end. It's just the single particle the type binding Hamiltonian that you use to construct these scalar bands. It's not really an interacting Hamiltonian. So if you want the interacting one, you need to project after that, right? You need to consider density interaction and then project that, right? I guess that's
right. Yeah. Well, okay, I'll send you the papers.
Thank you very much. Thank you.
Yeah.
Do we have more questions? Okay, so if no question, let's thank Bruno again for this very wonderful talk. Thank you.
Thank you so much for the invitation. This was very nice.
Okay, we'll see you next week. Bye.
Bye-bye.